Okay, hello everyone. I'm Haojie. It's a great pleasure to be here and share our work. Title is UniSense, the Spatial Uncertainty-Aware Collaborative Sensing Selective System for Autonomous Driving. This work is work with Professor Yanyong and Professor Wuyang and Xinran Lu. We will came from the University of Science and Technology of China. And Shuyao is coming from the Chinese University of Hong Kong. Firstly, let's begin with some background on the motivation. In recent years, self-driving has achieved remarkable progress and is gradually moving towards the commercial development. However, a self-driving system typically has a few key modules: sensing, planning, and control. The sensing module processes the raw sensor data and help virtual to understand the environment. It plays as the foundation of modules and is important to the overall performance of self-driving system. However, despite the recent progress, the single vehicle sensing still faces huge challenges. As shown in the figure, the left side displays a top-down image captured from above. This is a minibus and equipped with a LiDAR sensor. And here you can see its point cloud. In this scene, the vehicle is only able to detect the nearest car in the bottom left corner. The perception is missing due to the occlusion by the sharps, so there is no valid point cloud data there. In the upper right corner, due to the great distance, the point cloud becomes sparse and resulting missed detection tool. The important is what the car can't see may hurt us. However, this issue is arising from the physical limitation of sensors. And no matter how much single vehicle perception technology advances, it can't not fully resolve them. So, collaborative sensing allows the vehicles to share data with each other, which help overcome individual limitation and improve the precision, accuracy, and the range. By incorporating with the roadside unit data, vehicle can achieve longer distance range and the smaller blind spots. So as we can see, individual sensing is inherently limited and collaborative sensing is powerful. In this paper, we propose UniSense. It's the first special uncertainty-aware collaborative sensing system, and it enables efficient and high-performance sensing. Next, we will provide the description of our system. To make this passage clear, we organize the discussion around the key challenges and the corresponding solution. So the first challenge is the sensor input difference, which include both different in the sensor's hardware and their installation. For example, today's LiDARs come in many forms: solid state and fresh ice, and they each produce a different type of point cloud. Additionally, there are huge differences in LiDAR installation, such as the location. Vehicle-mounted LiDAR are typically installed at around 1.7 meters, while the roadside LiDAR can be mounted between the 3 and 10 meters above the ground. And this difference makes the raw point cloud data inconsistent across vehicles. So, simple fusion ROM is ineffective and may even degrade the sensing performance. To handle this, we don't fuse the raw point cloud directly. Instead, we go with the BEV future fusion approach. Specifically, we divide the point cloud into grid on the BEV plan, and then we use the sparse 3D convolution to extract meaningful features for each cell. This method offers three key advantages. The first is that it provides a unified spatial representation. It projects multi-view data into a common BEV plan, allows efficient, effective, and consistent spatial reasoning. Second is easily to scalability. The BEV format allows for integration of features from multiple sensor or platforms. Third, in collaborative sensing scenarios, BEV fusion has great potential to deliver higher performance compared to the zero-point cloud fusion method and the object-level fusion method. The second challenge is the communication bandwidth constraint. Today, the DSRC method can give us about 27 megabit per second, and 5G can go up to the 100 megabit per second. But there is a problem is, if we try to send 8-line point cloud at 10 Hz, that already take around 300 megabit per second, and the sending feature map could go beyond 700 megabit per second. So clear, current technology just can't handle this kind of data load. So to reduce the communication overhead, one intuitive idea is to only exchange the data for the selected region instead of the full region. However, this approach comes with its own challenge is how do we know which region actually needed to be exchanged? In many self-driving systems, people will often use occlusion detection to figure out which region might lack sufficient information and need more data. This indeed provides an process solution. However, is it enough to just consider the occlusion? Oh, our answer is no. Detection performance can be impacted by various other factors beyond occlusion, such as the sparsity of the point cloud and the abnormal distribution of point cloud, and the background may have a similar distribution with the vehicles. So that's all cause the error detection. So here, we proposed a spatial-uncertainty assessment method to evaluate whether each region requires more data. First, we use an occupancy head to predict the occupancy status and the semantic class of each cell. Then, we compute a spatial uncertainty map by cross entropy. Based on the uncertainty map, we propose a minimal yet efficient communication way, which is request only what is needed, just share only what is observed. In other words, vehicles request data only in the regions with large uncertainty, and only return the data within the areas with non-zero occupancy probabilities. Going a step further, we propose a method is to trade time for more bandwidth. In traditional collaborative sensing strategies, a sequential interaction method is typically adopted. We assume that both vehicles on the roadside unit get point cloud at the same time. After that, each site will propose the data individually. And the vehicles then send a data request to the RSU based on its uncertainty map. When receive the request, the RSU process and return the required data, which is subsequently fusioned on the vehicle side and output the detection results. However, this pipeline is total reached 130 millisecond, which is more than the real-time constraint of 100 milliseconds. In this work, we propose a parallel data extraction strategy to make this. We maintain a cache to store data received before. After finishing local data processing, the vehicle still sends the data request to the RSU. However, instead of waiting a response, it reads the corresponding data from the cache. So this way allows us get a shorter processing cycle. It reduces the cycle from 130 millisecond to 60 millisecond. And it could increase the max communication throughput from 36 to 75. Finally, there is also an issue of time misalignment caused by the data transmission. As shown in the figure, if we directly fusion the misalignment data, it can lead to detection error. Here, and we propose a method called selective motion synchronization. The key idea is we just only need to only few self-driving scenes contains moving object, even less than 5%. So indeed, predicting the motion for the entire future map, we only need to predict the region with the object. Finally, our system flow has 4 steps. The first is each vehicle extracts the behavior features from its own point cloud, and then it performs the uncertainty estimation and requests data from the nearby vehicles or roadside unions. Once the data request is received by other vehicles or roadside unions, there are returned the data, and finally, the requesting vehicle perform the data fusion locally and output the detection result. Next, we will talk about the test setup and the evaluation. Actually, we built a vehicle infra collaborative sensing platform in our campus. The platform includes a self-driving minibus with a RTK GPS and a multi-LiDAR sensor, and could let it get the 360-degree perception. And the minibus also has a communication unit to perform the data process and the detection and the planning and other. And it also has a 5G CPE device to communication with other vehicles and the roadside units. On the roadside, we deployed 16 smart lampposts, each with 32 line or the 80 line LiDAR sensors and the GPS for synchronize for all the roadside device. In addition, we built a collaborative dataset with more than 8,000 frames, which are labeled by human experts. Finally, we will talk about our test result here. We showed the effectiveness of the uncertainty evaluation in our scenario. The left figure is showed the detection result based on the point cloud, while the right is the correspond the uncertainty map. As shown, regions with the occlusion regions with occlusion have higher uncertainty, and the more than is object with inaccurate detection result also has more uncertainty. Here is a comparison with the excited method after time synchronization. Our method also achieved the best performance. This is the overall sensing performance. Our method also achieved the good performance in perception, common to the SOTA method. It is showing the cost of each modules with the total end-to-end latency around 16 milliseconds, which is meet the real-time constraint. This is the communication overhead, which is within the max limitation of 75 megabits per second. Finally, we show the gains from the collaborative sensing. It can mitigate the issue of the misdetection, and it can improve the perception range. In summary, in this work, we propose UniSense is the first collaborative sensing system that uses spatial uncertainty evaluation to guide the worker to data sharing and fusion. It can improve the perception range, accuracy, and communication efficiency compared to the SOTA solution. And finally, we released the collaborative sensing dataset. It consisting more than 3,000 pairs frames and a total of more than 8,000 labeled frames. Okay, that's all. Thank you for your attention. Okay.
Hello, this is Peng from Zhejiang University. Thank you for your presentation. My question is, currently your work is focused on the LiDAR sensor from different car. So I'm wondering if your method could be adapted to different sensor. sensor, and it is possible to use different sensor from different car in the future work. Yeah.
Okay, this is a really good question. The answer is our method can adapt to the different sensors, such as the camera and such as the radar. Our method is easy to general across different sensors, because it's designed is task driving and it don't have the relation of the input models.
Okay, thank you.
Okay.
Hi, this is Yang from Colorado School of Mines, and I used to work for Xiaopeng. And so my question is, in practical, what is your vision of implementing this type of like communication in real world scenarios? Because like, you know, different companies, they have their own autonomous driving algorithms, and how you put together these things. Because like your system require like kind of like requesting data from other vehicles. But what if the vehicles are from other companies? So so in practical, like what is your vision of like solving or overcome this kind of like issue?
Actually, can you say it again? And just slowly a little.
Oh, okay. So basically the question is like, you know, in many countries we have like different companies building cars, and they have their own autonomous driving algorithms. And it seems like in your approach, you are assuming like, for example, all the cars are Tesla. So then you can easily request the data from the sensors from other vehicles. But what if in China, like you have different brands? And what's your vision or suggestion of like overcoming, or simply speaking, like putting your system into market?
Oh, that is a very good question. And actually, this need the government driven maybe, and maybe such as this, like ours, and can't do more thing about this. But I think that finally, the collaborative sensing maybe is a future way, because it really improve the perception performance. I think in today it's like the comp relation among this business, but if we the advantage in some steps, in some strategy, they may collaborate together. Yeah.
Okay. Thank you.
Okay.
Yeah, let me just follow up on that. That's actually a question we've been thinking ever since 2018. This is a long-standing question. And I just want to share a few thoughts of mine too, if you don't mind. Really, it's challenging to enable this across companies, but you may already see Waymo cars has been deployed in San Francisco, Los Angeles. They encounter each other all the time. Don't even need to mention Tesla is even more pervasive. Sorry. So actually, I bring my lab mates, lab students for an outing in Santa Monica last week, and I asked them to experience Waymo, and one of them say they see this kind of capability already implemented. I cannot verify, right, because I was not in the same car, and I know some of the friends who's in this space actually is researchers in Waymo, so it's highly possible it's already implemented. Okay. Any other questions? Okay, we're right on time. Thank you. Let's thank speaker again.